So what do you remember from what we talked about at the beginning of the year, or anything you talked about last year, about inverse functions? Or actually, I'm going to say this now, and we'll talk more about this later. It actually doesn't matter if it's a function or not, as far as the calculus stuff goes that we're going to do. It could just be a relation. It could be an implicitly defined relation like we've been talking about before. We could be dealing with a function that doesn't have an inverse that is a function. And we'll talk about how we'll deal with that. But I just want to know, what do you remember about any of that right now? Nate?
Its graph is mirrored over y equals x.
Okay, good. So the graph of the inverse is mirrored over the line y equals x. Good. Melissa?
Find the inverse, you have to, like the x and the y, have to switch spots.
Okay, good. So if we have a graph of an inverse or an equation of an, if we have a graph of a function or a relation, or the equation of a function or a relation, and to get the inverse, then we just switch x and y. And that's actually why we end up reflecting it across the line y equals x, because we're replacing every x with the y and vice versa. Okay, what else? That's about it, right? Let me ask this. When will a function have an inverse? So let me give some examples here so I can be a little more clear about the question that I'm asking. Let's say we have the function y equals x to the third power. Does that function have an inverse? First of all, is that a function? Yes. How do we know something's a function? Vertical line test. So if we were to graph this, and I think we all know what the graph is going to look like, right? At least somewhat. So if we graph that function, we get something that looks like this. Yeah? You agree? Okay. So then how do we know if it is a function? How do we know if it is a function? You guys just said it. Vertical line test, right? So if I am able to draw a vertical line that does what? What has to be true? Let me rephrase that. What has to be true about any vertical line that I draw on this graph? It only crosses the curve the graph wants, right? And in this case, is that going to be true? Is that going to change if if I expand the domain here, I widen my graph, is it still going to be true? Yes. Yeah. If I go out to bigger x values or bigger y values, I'm still only going to get those vertical lines crossing the graph one time. So does this graph then, or this function, have an inverse? And what would it look like? Well, do you guys want to do it graphically or algebraically to start? Graphically? Okay, so if we were going to flip this over the line y equals x, what would it look like? Here's the line y equals x. Somebody describe it for me. Just flip it, right?
It touches the origin.
Okay, it is going to touch the origin. That's a great point. So let me draw the inverse here on this graph. It is going to go through the origin. Let's flip this part right here, this branch. Okay, instead of going straight to the right, I'm going to go which way? Cool.
I'm gonna go up a little bit.
Go up and then which way?
And then right.
Up and to the right. Okay, good. So the new graph is going to go like this, somewhat, right? You guys agree with that? That would be a mirror image across that line, so we would get something that looks like this. And then the other branch? Down and to the left. Something like that, right? You guys agree with that?
Correct.
Okay, cool. What if we wanted to do it analytically or algebraically? What do we do? Switch the x and the y and then solve for y. We want to get y by itself. So to do that, we would use the cube root, and we would get y equals, we could write it one of two ways, the cube root of x like that, or we could say x to the 1/3 power. Okay? So this right here, if we were to graph this, would look like that. You guys agree with that? Okay? And are there any problems here with this being a function? Is this a function? Let's try the vertical line test. Let's see. There's one spot here that might be a little tricky. I think in most places it's pretty obvious it's only going to hit at one spot, right? What about right here? You guys see where I drew that last one? Right down the origin, or right down the y-axis. How many different y values do we get when we plug in x equals 0? Still only get one, right? Now, we might have a problem there. The reason we thought that we might have a problem there was because it has what kind of tangent line? The slope is undefined. It's a vertical tangent line. Even though it's a vertical tangent line, if we were to zoom in on this, we would see that even if we move just slightly away from the y-axis here, it's still not going to be the same value. It's not going to be 0 still. Or, I'm sorry, even if we move, yeah, that's what I meant to say. It's not going to be 0, so we're moving away from the y-axis as we move to the right. Even if it's not very much at first, we still get different values there. So this is a function also. All right, so the question is, when are we going to have trouble? When are we not going to get functions for inverses? How about this? What's the graph of y equals x squared look like? It's a parabola, right? So it's going to look something like that. Yeah? So then if we reflect that across the line y equals x, what's it going to look like? Do you agree?
Yes.
Kind of sloppy, but close, right? Is that a function? No. So we had y equals x squared is a function, and then when we take the inverse, we get something that's not a function. And if we do this algebraically, we'll kind of see what's happening here. The inverse, we're going to get x equals y squared, so then to solve for y, we get y equals the square root of x, or when you take the square root, what do you have to do? Yeah, it's going to be plus or minus, so it's really going to be plus or minus the square root of x. So we can plug in an x value into this, and we could come out with a positive number or a negative number. For example, if we put in 4 here, we went to 4 on the x-axis, we could get a positive 2 as our answer, or we could get a negative 2 as our answer. And that's the top half and the bottom half of this relation. So when we take the inverse of something like this, then what? It's not going to be a function. Okay? We know it's not a function because of the which test? The vertical line test tells us that the inverse is not a function. Okay, now, finally getting to the question that I was asking earlier. These vertical lines are hitting twice. So looking at the original function, how could I tell if that original function is going to have an inverse that's also a function? The horizontal line test. So the horizontal line test is going to look more like this. And if the horizontal line crosses the function more than once, then it's not going to have an inverse that is a function. Does that make sense? Okay. Now, after all of that, I'm going to say this again. It actually doesn't matter if our inverses are functions or not. And the reason it doesn't matter is because we know how to do implicit differentiation. And with implicit differentiation, we can take the derivative of a relation even if it's not a function. So all of those properties of inverse functions that we've talked about, they're going to apply to relations whether they're actual functions or not. Okay, so we still replace x with y. We still flip it over the line y equals x. Okay, now one of the most important things that we're going to talk about is calculus related. Okay, this is just stuff that we just talked about. So we're going to replace x with y. One important thing that we didn't really hit there, on the original relation and on the inverse, there are going to be corresponding points. And to get to the corresponding point, what do? Let me go back to the picture that I had. I lost my picture. There it is. Let's say I want to know what point corresponds to -2, 4. I'll call that point A. What point corresponds to that point on the inverse over here? What do you say, Ethan? 4, -2. So if we go to 4, -2, I'll call that A prime. Not because it's a derivative, but because it's a reflection of that point. So usually we use that prime to represent a new version of that point. And that would be at 4, -2. And how'd you get that, Ethan? Yeah, just switch the x and the y. So these 2 points would be what we would call the corresponding points. And they've got an important property that's going to deal with the calculus side of inverses. And it's something that we kind of started talking about yesterday, and we'll get into it a little bit more depth today. Any questions so far about inverse relations? All right. It really doesn't matter what this is, what function it is, but first of all, is this function going to have an inverse? That is a function. Let me ask a better question. Is this function going to have an inverse that's also a function? Yes. Why? Yeah, it passes the horizontal line test. You can draw horizontal lines on this, and none of these horizontal lines are going to cross more than once. What if it doesn't cross at all, like that bottom one? Does that mean it's not a function? No, it doesn't really mean anything, right? So what's the inverse going to look like? What would I do first? Okay, I would draw the line y equals x. That'd be a good start. So there's the line y equals x. And then how do I figure out what the inverse is going to look like? Just flip it over that line. If you're a good visual, spatial mind person, you might be able to do this pretty easily. If you have trouble with that kind of stuff, you may want to just plot a few points and then connect the dots. If you want to plot points, you could look like here. The point 0, 1 would go to where? 1, 0. I know we don't have any other clean points, but we have a point here that's at -3 and just a little bit bigger than 0. So where are we going to get a point on the inverse? Perfect. A little bit bigger than 0, 3. And then on the other side here, we have a point at 1 and then a little bit bigger than 2. So we're going to have a point at... Yep, a little bit bigger than 2, 1. So a point like right there. Okay? And notice that each one of these, we reflect it across this line here. So we go to the line of symmetry and then keep going. Go to the line of symmetry and then keep going the same distance. So we can just take these points here and reflect it across that line, and when we connect the dots, we get a graph that looks something like that. Yes?
So as long as if the original function passes the horizontal line test, then its inverse is also a function?
Correct. Yes, good. Okay, does anybody know what these 2 functions are? Does anybody know what the blue function is? it is the exponential function, more specifically, and it's not immediately obvious from the picture, but it's e to the x. Okay, it could be a graph of 2 to the x, but I know it's not that because if it was 2 to the x, then we would have a point at 1, 2 right here, and it doesn't quite go through that. So the blue function is e to the x. How about the red function? That is the natural log function, yeah. And it could be any log function. This one just happens to be the natural log because the natural log is the inverse of the exponential function with e as the base. Okay, so we end up with a picture that looks like this. And so let's start talking about the calculus side of this. Let's say I pick a point here. It really doesn't matter where. Pick this point, and I want to know the slope of the tangent line. I'm not concerned about how to take the derivative of the exponential function. We're actually going to deal with that later. I'm more just concerned about how we find the slope of the tangent line. How would we find the slope of this, just generally? How would we find the slope of this line right here? Take the derivative, right? And then what will we plug in? Yeah, whatever point that is, whatever x value it is, right? So if we took the derivative, we'll call this point C right here. Then the slope of this line, let me be a little more specific, the slope of this line is equal to the derivative of f, and we'll call this function f, at C. Okay, you guys agree with that? That's kind of what we've been talking about for the last 3 weeks now. The question now, though, is what happens at the corresponding point? So, first of all, the corresponding point, we could get a couple of different ways. I'll just reflect it across the line here, and we get the corresponding point here. And if I have a tangent line at that corresponding point, like that, how do you think we could find the slope of that knowing what we already know right now from this function? How do you think, and the question is, how do you think the slope of this line compares to the slope of this line? Are they the same? No, I think it's obvious they're not the same. Are they opposite reciprocals? Are they perpendicular to each other? No? Anybody remember what they are? We talked about it yesterday, didn't we? Yeah, they're just reciprocals, right? So the slope of this line right here is equal to, how would I write that mathematically? Well, 1 over this m, which is... Okay, so the slope of that line is just going to be the inverse or the reciprocal of the slope of this line. Now, here's where it gets a little bit tricky. How is C involved in this point right here? Is C the x value?
No.
No, this is the x value of C right here. So how is C involved in this point? It's the y value. So it's the value of the function at that point. So this right here is C there. And that's how it ties in to the slope here. Okay? This idea here is actually going to be kind of powerful for us when we start doing derivatives of inverse functions. It's going to allow us to work with inverse functions without ever really knowing what the inverse function is, which can be very useful if we're dealing with kind of crazy functions that are hard to actually find the inverse, that are hard to solve for y when we replace x and y. So this is a really useful idea for us in a lot of ways. So we've got the same idea here. I could draw the tangent line on the A prime, which would be the corresponding point. And you may also notice that the two tangent lines, the tangent line to the original relation and the tangent line to the corresponding point of the inverse, go through where? Where do they intersect? Yeah, they intersect somewhere on this line, and that's actually always going to happen. That's a property that can be useful. We won't use it much, but it is something that could be useful if we were having trouble finding a derivative in some way, or we might be able to use that kind of as an in between to find some information that we need. Okay, so some important things to note. First of all, every point on the function has a corresponding point on the inverse. I'm talking about functions here, but the very last thing that I put on here, the same properties will apply whether we're dealing with a function or if we're dealing with a relation. Okay, so all of these are going to work if they're a function or a relation. I'm using them in terms of a function here, but it also works if it's not. The slope of the tangent line at any point on the function is a reciprocal of the slope of the tangent line at the corresponding point on the inverse. And that's the calculus idea here that we need to get from this. Okay, that's what we need to take away as far as calculus goes. Any questions about that stuff? I'd like to do this example a couple of different ways. So my goal here is to find the slope of the line tangent to the inverse of y at the point 16, negative 4. So this is our function, y equals x. What do we know, first of all, about the inverse of this function?
Not a function.
It's not going to be a function, right? So the inverse of this is not going to be a function. That doesn't mean we can't do it, though. All right, so let's start by just figuring out what the inverse is going to be. And what I want to do is I want to approach this problem the way we probably would have before our discussion today, and then look at how our discussion today might help us simplify the problem. So what would be the inverse? How would we figure that out?
X equals y squared.
Okay, so we're going to start with x equals y squared. And remember, this y here, that's actually the inverse y. Just keep that in mind. We might call, well, it might not be a bad idea to use some sort of notation to show that's the inverse. I'll do that here when we solve for y. So what do we get y equal to here? You guys know this because we already did it. Plus or minus the square root of x. Good. All right. So first of all, if you notice here, if we put 16 in for x, we actually get two different values, don't we? What are the two values that we get?
Positive 4 and negative.
Yeah, we get positive 4 and negative 4, exactly. So in this particular problem, I had to give you the y value also so that you knew which one to use, because we get two different points here. So when x equals 16, you get a point at 16 positive 4, and you get another point at 16 negative 4. To show that this is the inverse, we'll go ahead and just put a negative 1 up there. So the inverse of y equals x squared is going to be plus or minus the square root of x. Now, since we're dealing with the negative part of it, and we want to find the slope of the tangent line on the negative part of it, when we take the derivative, do you think we have to take the derivative of both the positive part and the negative part? We actually don't need to. When we take the derivative here, we're just going to take the derivative of the bottom half. So we're going to just take the derivative of this part right here. If we were trying to find the slope of a tangent line to the top half, we would have to take the derivative of the top half. If we wanted to do it generally, we would have to do both and then combine them. And we might be able to combine them kind of neatly. We might have to write it as a piecewise type function. So how would I find the derivative of this? Any ideas? Give me 1 second here. So we want to take the derivative with respect to x of y prime. I'm sorry, not y prime, of the inverse of y. Haley?
Couldn't you change it into exponential form?
Yes. So I would definitely do that. So instead of negative square root of x, we would write negative x to the what'd you say? 1/2, yes. So then the derivative of the inverse is going to be what? What can we use here? Yeah, we can use the power rule. So, Alyssa, did you start saying it?
Yeah.
Okay, go ahead.
Negative 1/2 x to the negative 1/2.
Okay, negative 1/2 x to the negative 1/2. Let's switch it back to radical form now. And what would we get then? Negative 1 over...
Negative 1 over 2 right edge.
Yeah, I would say square root though, because radical could be any power, right? Or any root. Okay. So we get negative 1 over 2 square root of x. And remember, that's the derivative of the inverse. So then if we want to find the slope of the tangent line, so we'll say the slope at this point, 16, negative 4. What are we going to get? How do we do it? Hmm?
Plug in 16.
Yeah, we'll plug in 16 to x here. One thing I want you to notice, this 16, negative 4, that's a point on what? Is that a point on the function or the inverse? That's a point on the inverse, yeah. And if you're not really sure, you could plug it in and see what happens. If we put 16 in for x here, we'd get 256 for y, right? And that's not quite equal to negative 4. I know it's close. So this is a point on the inverse, and since we took the derivative of the inverse, we're going to put the x value in from the inverse to figure out what the slope is there. And 2 times the square root of 16 is 8. So the slope of the tangent line to the inverse, tangent line of the inverse, nope, didn't say that right either. The tangent to the inverse at the point 16, negative 4 is going to be negative 1/8. Okay, everybody good with what we did there? Is there anything we did there that you wouldn't have been able to do already? Before our discussion earlier. Yeah.
Okay, so explain one more time why you took away the positive square root.
Okay, good. So let's look at the graph here real quick. So the graph of the inverse is going to look like this. So you're going to have the positive square root part and the negative square root part here. And the point we want, the point we're dealing with is at 16, negative 4. So it's down here, right? So what we want then is the slope of the tangent line at that point, so the slope of this line right here. Okay? Since we broke it up into the positive part and the negative part, and we want to know the slope of the tangent line at a point that's on the negative part, then all we have to do is look at this part here. And the top half of this doesn't really matter, so we can just get rid of that. Does that make sense?
Yeah.
Okay. If I were to ask you to find the derivative of the inverse of y equals x squared, you would have to actually do this for the top half and the bottom half. You would have to do it for both. Since this problem is dealing specifically with a point on the bottom half, you only have to deal with that one. Okay? All right, so, do you have a question?
Why did you, does the question ask, is the point on the inverse function or is it on the regular function?
Are you asking me?
Yeah.
Didn't I ask that already? Well, if you're not sure, if you get a question like this and you're not sure if that point is on the inverse or the original function, just plug it in and see which one it works on. 16, negative 4, if I put 16 in for x here, 16 squared is 256. and we have y equals -4. So is -4 equal to 256? So, yeah, so that's not a point on the original function. If I plug it in here, put 16 in for x here and -4 in for y here, this is the inverse, we end up getting a point that works here. Which means that 16 -4 is a point that's on the inverse, not the original function. Does that make sense? Okay. Okay, so what I want to do now is take our discussion, what we talked about earlier with the calculus side of inverses, and do this problem a little bit more easily. We know that every function has a corresponding point on the inverse, right? So this right here, this point, is on the what?
Inverse.
On the inverse. So on the original function, oops. What point's going to correspond to that? I'm going to put that on there so I know it's on the inverse. What point corresponds to that on the original function? -416. Okay. Now, I know that the derivative at this point on the original function is tied to the derivative at this point on the inverse function. So what I'm going to do is I'm going to take the derivative of this. What is the derivative of x squared? Okay, 2x, you agree with that? Everybody agree with that? All right, now I know again that the derivative on the original function is tied to the derivative on the inverse. So I'm going to evaluate the derivative of the original function at x equals -4. Or I could put, I'll just put this point here, -416. And I get what? -8. And I want somebody to complete this line of reasoning here. So I know that the derivative of the original function at the corresponding point is -8. So how do I find the slope of the tangent line to the inverse at 16 -4? Take the reciprocal of that. So the derivative, well, I'll do this. The slope, the notation here would be kind of tricky. The slope that we're looking for, which would be the slope of the inverse at 16 -4, is going to be 1 over -8 or -1/8. Now I don't know about you guys, but I would rather take the derivative of x squared than taking the derivative of the square root of x. Does that make sense? Now this is a very simple problem. It's a problem that we could do either way, and it's still fairly straightforward. There's a chance that we'll run into a function that we really can't take the derivative of. And then your options then would be to use implicit differentiation once you switch the x and the y, or to take the derivative at first and then find the slope at the corresponding point and take the inverse of that, the reciprocal. This example is actually a typical AP test type example. So for this type of thing, it would be a good idea to start with what you want to find and then see how we can get there. So we want to find the derivative of the inverse at the point 5, okay, at x equals 5. So if we take the derivative of f and then if we take the inverse of f and then take the derivative, I want to know what that derivative's going to evaluate to at the point 5, at x equals 5. What do I know that can be helpful here?
The derivative of x equals 5.
Okay, this right here?
Yeah.
That would be what I'd call a red herring. You guys know what a red herring is? Yeah, it's the design is to the idea of a red herring is to distract you, and actually they use red herrings in hunting. They would drag red herring scent across a trail to throw off the dog's scent. That's where the term comes from. That's actually absolutely useless in this problem. Not going to help us at all. Sorry. Anybody know why? Okay, let's look at a couple of things here. Just some information that I know, and let's start with this. Did you figure out why?
Because the inverse isn't gonna have a point at, or the point at x equals 5 isn't gonna be the same on the inverse.
Right. So remember, when we go to the corresponding point on the inverse, we're going to flip the x and the y. So this point here at 5, 1 on the function is going to become the point 1, 5 on the inverse. So what this derivative tells me is that the slope of the inverse at x equals 1 is going to be negative 1/2. It's going to be the inverse of this. Okay? So it would help me if I wanted to find the derivative of the inverse at 1, but it's not going to help me to find the derivative of the inverse at 5. So which point is going to help me with that? There's only one other point up there. So this point at 2, 5 is going to have a corresponding point on the inverse at 5, 2. Okay, now the slope of the original function at 2, 5 is what?
3.
Okay, so the slope of the tangent line at this point is going to be 3. So what's the slope of the inverse going to be? So then what's this? 1/3. Okay, one other question about this situation. What is the equation of the tangent line to the original function at x equals 2? So the equation, that's a g. Equation of tangent line at x equals 2. Alyssa?
You can just use the slope, which is 3,
Uh-huh.
and use 0.25.
Perfect. So the information that we need for that is right here. And the reason I ask this is a lot of times when I give you a situation or equation for a function, you find the derivative to find the slope, and then you plug the point in to find the value of the function at that point, and then you use those two things to write the equation. It's interesting, and this is something that happens across the nation. It's typical on AP tests for this question to be given with this information, and students get it wrong. So when you want to write the equation of the tangent line at a particular point, these are the two things you need to know. You need to know the value of the function at that point. You need to know the value of the derivative at the point. This tells you the slope right here. This tells you the point. And so all you have to do then is write the equation. Y minus
5 equals 3 times x minus 2.
Yeah. So if you're ever asked to write the equation of a line, you need to know the slope and you need to know the point, and that's what the function and the derivative give you. So don't try to make this type of problem any more complicated than it is. If you know the slope and you know the point, then you've got your answer. You just need to put it in the right form.